So as I mentioned in the opening, we are switching gears a little bit now and talking now about a set of things that we here at UW have been thinking on. These are not necessarily things we'll pursue as far as center, but we thought we at least share our thinking. Of course, what we do end up depending on feedback from this group here. But I must say, I think just looking back at the talks from pre-lunch ones, I think whenever I listen to talks like that, he says, I wish I could do everything. All of those problems are so interesting and so challenging both, and so rewarding if you get them right. But of course, you can do only so many things in life. So anyway, with that setup, I'm going to talk about this one dimension we've been kind of thinking about. I have done a little bit of work, but this tries to kind of bring it together. It's what we are calling application-defined networking, and a bunch of us are involved, and as well as a lot of students as well. So here's the kind of context. I think over the last half a dozen years, I would say, or maybe something that range, like when systems people like me and others were not looking, an entirely new class of networks has emerged. You can call them application networks, and they look very, very different from infrastructure networks that we are used to thinking about, right? So what these application networks are doing, they aim to connect endpoints on an application. They don't try to connect anybody unknown, to anybody unknown. So the general principle around host attachment, so that's not what they're trying to do. There's a very specific goal to these networks that I'm going to connect endpoints of an application. The other thing that's very different from infrastructure networks here is that they need very, very rich message processing. What really happens as a message leaves one endpoint of the application to the other? It is going to get load balanced. Is it going to get secured? Is it going to get access controlled? Is it going to get compressed or not? So what they're asking is not just IP. The other key distinction here is that these are networks that are built by application developers, and they are not being built by network engineers. What I really mean by that is application developers have very different expectations from networks with respect to testability and debuggability. Traditional network engineers are masters of complexity, in Scott's words. I think they can deal with a lot of stuff. It's just amazing how little patience software developers have for the kinds of things that network engineers just do day in and day out with respect to things. So I think that's kind of expected as well there. So what's really driving these class of networks? And I'll talk a little bit about the states. Like, these networks are now everywhere. What's really driving is that there has been a fundamental change in how high-performance applications are constructed. There was a time when you would write like a big piece of, be it Exchange, be it database, be it web server, and so forth. You'd basically put it on a beefy server. What has happened now is that almost all new applications are being written as distributed microservices. And there are huge amounts of advantages to the application developer and the company to actually constructing the applications this way. For starters, you can scale these services independently. These services could be written in independent languages, makes it easier to reuse third-party code, makes it easy to actually control the blast radius of your application, and so to speak. So what is getting the developing team here is huge amounts of agility, huge amounts of code reuse, as well as a level of kind of operational ease that is difficult to have with a monolithic application. But it's all not all, not all roses. But once you've ripped apart your application, you need to start worrying about things that were easier to deal with. You need to worry about security of messages now that are going over the network. You have to worry about access control. You have to worry about observability, telemetry. You have to worry about load balancing and who can talk to who and so forth. Essentially now you, as the app developer, has to worry about things that the network was doing for you. In other words, you have to build your own network, and which is what application developers have been doing with the help of these things called service meshes. The need has been so acute that organically almost, more service meshes have emerged in this world than the number of people in this world. These are maybe just kind of half the logos that I could have collected here. Every single large software company that you may think of has a service mesh offering. And the reason these are kind of, I already talked about like why they are kind of taking off. And to just give you stats, like today, 90% of organizations reported to CNCF, they are using service meshes in production. or they will be using it next year in production. So basically, all applications I'll be rating, they're all using service meshes today. So that's basically, think of this as like what, native cloud application development world looks like today, right? So that's all great, and they are enabling you to build what we're calling application networks. So this is where the story takes a turn. Like, what's wrong? So service meshes, this is, I think Kelsey is DevRel, developer relations person at Google. So it begins to capture some of the pain points around there. Like, essentially what this code here is capturing one pain point around the compute resources and the resources these service meshes take today. There's data coming out of Facebook and Google that basically says that microservices communication layers are consuming about 20 to 80% of CPU cycles. 20 to 80%, think about that for a second as to, and this is just enabling kind of that network in there, right?
So what was that 20 to 80% of what?
Of CPU cycles. Yeah, right, yeah. So basically, if you do the math, the real application logic is actually consuming subfractions, right? But of course, you don't, you're scientists, you don't trust third-party numbers. So I think Changfeng here is in the back. We did our kind of our own experiments on a bunch of benchmarks, and these are just quick data from some of these experiments. What this data is showing, using the Envoy proxy, which is one of the most popular ways to build these things, what the gridded bars over showing is like the overhead in latency and CPU usage that service meshes are adding today. This is one benchmark, and we've seen this across multiple workloads. And what you see here is that, for some of the queries, service meshes are actually adding 2x the overhead. So, if your application has latency x, start using service mesh communication there, it becomes 2x or more. If your application is consuming, 2 virtual cores, it may start consuming 4 virtual cores because of the way you're kind of doing these things, right? Yeah. And that's not the end of it. Well, I'll explain that, but for those of you who don't know why this is happening, it's happening because fundamentally this is how service meshes are being architected today. What really happens is the application service, microservice here, S1, it sends a packet unbeknownst to the fact that there's a service mesh running underneath. The packet goes down the network stack, goes down to the IP layer where it gets intercepted and in the kernel space and goes back up to user space. That blue thing here, this is the proxy. All the network processing that you need that is custom to the application happens in that little blue box. And then the packet goes back down again, sent over at the receive side, the same thing happens again. This little proxy here knows that this little proxy is running, so it can reverse the effects of the sender and hide its existence from the application. And then, packet goes up to user space, packet goes down, and then hands over, and then service mesh essentially S2 takes it. So that's essentially what's happening and how application networks are being built today. But it's not just about that. I think that is one key piece of it, of course, that packets are going up and down the stack, as a result of which you have long code paths. You're doing a lot of duplicate work. In fact, we are finding, service meshes, proxies, they are parsing HTTP, and of course, that gets, deserialized, it gets parsed again and again by the application. So that's essentially where your CPU cycles are going, and that's where that 2x latency is coming from in there. But it's not just that. If you try to optimize the current architecture, my guess would be you would fail. You would fail because this proxy code is very, very complex. It is trying to be basically do everything for all possible application and communication message features. It's the anti-end-to-end argument approach to building systems is what's basically happening because software is easy to change, so you keep adding features to them. So as a result, you have code now that is very difficult to optimize. It's very difficult to inline, which is why it's running as a separate user space process, and nobody in their right mind will push that to the kernel because then the whole machine crashes and so forth. But also, it's very, very difficult to actually get any kind of hardware assist from that piece of code. And thus, all the investments that folks are making into accelerators and star PUs, in Dave's words, they are basically cannot be used at all with this architecture in place. Finally, I would argue one other point that fundamentally the way these things are being programmed today is using the wrong abstractions. Application developers telling at the packet level what manipulation should happen for the features they want. At the same time, to specify network processing, They are basically specifying individual proxy actions. You know, if this packet comes in, send it here, type of things, like, you know. What that does is that it becomes very difficult to specify intent. You have, the underlying infrastructure has no idea what should be happening, and it becomes very hard to optimize processing. This was like one of the crux, for instance, Bhaskar's talk this morning around, you know, how do you optimize application communication if you know very little about the application, and that's what, so it's hard to do and hard to optimize before. Okay, so here's what we can thinking. Yeah, Rodrigo.
I'm slightly confused by the last point, because I would imagine that because you have these proxies, they're layer 7 proxies, aren't they dealing with application level messages and not packets?
They are dealing with, but they've taken the packet away at the IP layer. So they don't understand what an application layer message was. They see an IP packet. You can reverse engineer and try to put stuff together, but that's what you would have to do. At the layer at which they intercept, it's an IP packet to them.
So the proxy is not terminating the first TCP connection and then creating another one?
It is doing that. It is doing that.
So the proxy sees
the proxy sees an IP layer packet, and the proxy does not know whether two IP packets are part of the same RPC or not. The proxy does not know what application protocol is running. For instance, you know, if you want to do MySQL optimization, so you can throw in today filters that would give you some kind of MySQL acceleration here, but the way those work is they'll have to reassemble the IP packets back, right? So there's no, all that information is lost, right? Yeah, but good question. Okay, so here's kind of our thought, what we're going to do. I think this is where the idea of like application defined, looking at the problems that way, that we would like developers to specify an entire network level intent at a high level in there, and using abstractions that are relevant to the application. In our concrete instantiation, we think these should be RPCs. Like, you know, 95% of data center traffic today is RPCs, and these applications like these, the specifications should be declarative and portable in there. So that's kind of the top half. At the back end of this, we want to be able to generate an optimized application-specific implementation. So we don't want to generate implementations that are general, but based on the intent and based on the deployment environment we're there. To the extent that we also want to generate message headers automatically. Like today, you know, for instance, when we come up with protocols, like, you know, the headers get thrown in, or you do this kind of very flexible key value pair stuff, and packets get bloated up, and then the other side has to parse all of that stuff, and a lot of CPU cycles go there. We think if we actually know the communication intent, we can actually even, for the first time, automatically generate headers. So the way one way to kind of think about this is like, I kind of mentioned end-to-end argument earlier. I look at this as a way to kind of cheat end-to-end argument, right? Like, I can give you, as a developer, infrastructure that is going to serve the needs of every single application, and I can have an implementation, though, that is not encumbered by having to meet the needs of all applications. So this is where I think using auto-generated code, program synthesis, and all the technology improvements that we can come and actually talk about redesigning the network stack in a way that is using now implementations like these in there. So how does it work? Just quickly, just so an idea of kind of what kind of we're thinking about. Is you have an application that says, you know, for messages going between my two services, S1 and S2, they should get load balanced, they should get logged, they should get compressed, and then, you know, I want to inject faults because I'm kind of in a testing phase, just as an example in there. So what are each of these things? Our thinking is each of these things will get expressed at a high level semantics like this, which is very analyzable, like, you know, and essentially you take RPC as the input, and you take some custom parameters, in this case probability. You can do processing that is based on the fields of the messages. So if we say, you know, if RPC version is 1 and my coin toss says less than the probability, drop the packet there. So remember, we have these building blocks. We automatically can compile these building blocks down to, depending on the deployment environment, to things like eBPF, to P4, to FPGA code, and so forth. So we've got these modules that we can actually run, but they're auto-derived from like a high-level spec. Once you have this, there are all kinds of cool things you can do now, right? you can automatically compose the right thing. You can first of all inline the code into the application because there, but you can automatically generate the right configuration. In this simple example, that means, if I'm compressing here, I must decompress here, right? Like today, developers will have to do it themselves. Like make sure that you've actually aligned these things. This is what I meant by wrong abstractions and proxy level actions and so forth. But things get really funky, and this is where I think, like going back to some of the stuff Bhaskar and others were talking about earlier. Like I can do things like this. I can, change the pipeline. So if you can pay attention, what's happening here is that I'm flipping fault injection and load balancer. I know it's safe to do it because I know what processing each of these modules are doing in code, right? Like, so I know, so I've reduced work because any packet that is dropped by the fault injector does not need to be processed by, logger, compressor, load balancer, and so forth. Things get more funky. Again, because I know the exact information flow in these modules, I can parallelize what I want. Like after the fault injector, there's no reason that logging, compressing, and load balancing, that processing should happen sequentially. I can automatically parallelize it, right? Or my imaginary compiler can, at least in theory. You can do this. You can move around where functionality is. And you know that you preserve semantics in some sense. That logging can happen there. This is, of course, assuming reliable communication, but I can move it there because I had better ability to log there. So all of this stuff that the network was doing and was basically completely set in stone can be done now as well. Finally, because I have a version of zip that runs in hardware, I can push it down there as well. The larger point here is that given a high-level spec like that, I can do all of this stuff that runs a lot faster and gives me all these opportunities for optimization that are almost impossible to have today. There. Does this make sense? Everybody with me? Mihai?
The problem was the service mesh doesn't trust the application. So if you move it down with the application.
We have a solution to that.
Yes.
Which is the next slide.
Yes. One more and then yes. Yeah. Okay.
We will answer this
Yeah.
question. Repeat the question.
Yeah.
I think the question, if I understood correctly, the service mesh does not trust the application. Is that the question? Yeah. So So I think I'll give you a short answer, and Tom will show some of the work. I don't think we've changed the trust boundary in some ways. Like, in fact, I think depending on how exactly you run it, this actually might be running in the application scope itself. Just a quick word on how do we kind of make it work? I see there's at least kind of three main streams of work. How do you do language design? And this goes back to the earlier point around bringing broad expertise together. How do you do language design, not just at this language design work at the top layer, what developers see. There's language design work on how these processing modules are specified so we can optimize them. There's work around compilers. How do you generate these processing pipelines? How do you target multiple platforms with these rich substrates? How do you optimize them based on application behaviors, based on SLAs and so forth? And in a minute, I think Tom will give two examples on the value you can derive if you were to do optimizations from deeply knowing application intent in there and deployment environment. But the fun thing is, if we do it, it doesn't stop there. For the first time, we would have declaratively intent on what applications are trying to do for cloud applications. So we can not just make the life of those applications better. You can actually, that enables you to do inter-application communication. That then enables you to do essentially where these applications should sit in the network in a way that's cognizant, so you don't have to reverse engineer the way I think some of the deployment systems do today. You can really improve and simplify underlying infrastructure as well, because you know what the applications want, and you can move things in and out from there. Okay, Ramana.
Yeah, so I think, this assumes that you have knowledge that service A will talk to service B.
Yeah, you have that, yeah, so I think you have this essentially.
Yeah, you know that,
right.
So that's where the intent comes from, but a lot of services are just basically, I provide a service to anybody with an API key, for example. How do you know which one is actually holding the API key to actually contact?
So these are, this is talking, this is not a client from outside of the service deployment coming in?
No, even within the application, right? Today I may actually have let's take a simple API service, right? I have 10 services that are talking to this.
Yeah.
I've given them the API key. The 11th service comes, I've given that the API key.
Yeah.
That has to somehow make it into the intent specification.
Mm-hmm.
If I don't do that, then in other words, as the application is evolving,
Yeah.
you have to always make sure that the communication paradigm is explicitly captured in your intent, right? And that works if it's a point-to-point A to B communication paradigm. But if it is a service-oriented, right? Like I can, as long as you have the key, you can access it.
Yeah.
So I don't need to control, right? Explicitly through a intent specification document.
So first of all, two things. Like today, you are controlling in some ways. If these are two endpoints of the same service, there is automatically what the service mesh is doing. It is somebody's telling things like either it could be Kubernetes or it could be something else. Like where's this service located? If I talk to the API holding service, you specify a lot today anyway. The other thing is that you can maybe, if you want, you can maybe fail open if for those kinds of things where you actually know nothing. But my answer to simple fix would be that if you have, let's say, API service that anybody can talk to, that's easy to generate the spec for. Let anybody talk to this particular service.
No, it's not anybody can talk to it. Anybody with a secret key can talk to it, right? And that you don't necessarily control because there could be hundreds of services talking to it. Mm-hmm. And then very quickly this intent specification will flow through the roof, right? If the application is sufficiently complex. Because now you're talking about quantifying every n choose k, communication things to be spec'd out as an intent.
Is it really that bad? I mean, it sounds like it's a little bit Corbett-esque. Like, okay, let's make this API spec now first-class object language again, and you can bring all this kind of structure and optimization there on. That seems reasonable. I do what you're saying is like, hey, in the microservices world, I've got an existing service cloud all going, and now someone brings in the 11th service. But it seems like some kind of just-in-time compiler optimization should also be possible there.
I'm not saying it's actually impossible to do. I'm just saying there's a burden associated with actually keeping the intent spec in sync with how the application communication paradigm is evolving. That's all I'm saying.
Yeah, no, I think I would agree with that, and possibly the transition here will help. So I'm going to talk about some other work that's not as spec-oriented, but yeah, go ahead.
Yeah, maybe, I think it depends on what level of granularity the intent is, right? Like if you're basically expecting intents to actually explicitly declare dependencies, then yeah, we have a serious problem. But if you can elevate the intent to, like what Ratul was saying at an SLA level, then identifying the dependencies actually becomes part of the infrastructure problem, right? And so I think the granularity and the level of the intent is pretty critical. Right? Otherwise, you basically end up with a crowbar and XML kind of a specification that's like, okay, I might as well write code.
Yeah, I mean, I think the other way of looking at it is this notion that what the application programmer is going to want, or the network programmer, this application network programmer is going to want, is something that's some portable specification of what they want to happen. And okay, some of those cases are going to be a service that you're offering to a set of users. Some of the times, okay, it's trying to connect your ML system to your data source or whatever else that might be, and that specification needs to live somewhere, and you need to actually think about how you're going to design the language for it. But at the same time, I think one of the other aspects of trying to get a more formalization of what those arguments are is that you can then drive optimizations down through the network stack. And so I'm going to talk a little bit about how we might go about doing some of this. So this work, again, as Ratul had said, is actually with a colleague of ours at Duke. And the basic idea is to think, oh, okay, if the systems are essentially like implementing service meshes, you essentially want to do something like a managed RPC. It's like you think of it as a software-defined network at layer 7. And this model over here is like how people do it today is like just treating it's okay, you've got your gRPC server over there, like generating packets that you're then unwinding. One strategy for addressing that would be to think, okay, what if we could replace that library that's packaging up our RPCs with something that's customized for the service mesh world. And I would say, oh, okay, we actually sort of understand how to do that. You actually want to pass these things through shared memory or some other mechanism. But you might not even actually need to marshal the packet at all. Possibly you might just need to be able to send over just the notion that I'm doing this RPC. Here's the scatter gather list for where to go find these packets. And then essentially your proxy then does the RPC marshaling for itself, can potentially customize that for the particular hardware platform that you're running on. And so, for example, oh, you have an RDMA thing next to it. Great, I get to customize it for that. Or if it's TCP, then you go in that direction. And in addition, you could potentially say, oh, okay, because I'm actually understanding how this thing is formatted, I could actually run the graph of processing elements against the RPC operations. There's a sort of similarity here, if any of you know how seccomp works in the Linux world, which is we apply policy at the level of system calls, not at the level of network packets. Okay, so that's like one model for this. And here's roughly what happened as we built this. So one of the things you have to be able to solve as a problem for that is this notion that the applications, which you might actually need to be able to support many applications that are connecting to the service at the same time. So as a consequence, I have to be able to change the bindings and the definitions of RPCs dynamically, have those instantiated in my service, which isn't really how the model for RPCs work today, and then be able to add extra modules in dynamically without having to reboot anyone, sort of like essentially be able to do dynamic live upgrade of RPC services. We can customize the marshalling code to be specific to the protocol spec that we have. So essentially, we're building a compiler that does that. And then you can essentially leverage in whatever SmartNIC support you might have. So as you increase the sophistication of the network hardware, this gives you a lever for why you're not having to build support for that in every application library everywhere. Anyway, so roughly speaking, because you're essentially eliminating these extra transitions somewhere between a factor of 2, factor of 6, performance improvement depending on how big your packets are, exactly what your workload is. Okay, so that's one model for how, sort of taking service meshes as the way we will go compute in the future suggests that there are optimizations we might do. So another thing that you can think is, okay, what lever do we have as a consequence of service meshes giving us visibility into network traffic? And then that potentially drives you towards thinking about how you might be able to get network SLAs for these application level operations, because you now have something that has visibility into what the application is trying to do and what it might be able to accomplish. So roughly speaking, on modern sort of under-managed network services, not necessarily hyperscaler systems, but in sort of more on-prem systems, you have a really large gap between what the performance you're going to get out of your RPC system in the sort of common case and what you might be able to get out of it in the worst case. And one question, like essentially one of the reasons for why service meshes are so popular is it gives you this ability to go have visibility. Okay, your performance really sucks today. Why did that happen? Oh, okay, you were doing some kind of incast that caused there to be some large number of packet losses, and your retries are just going to end up killing you over time. So your ability to have visibility in that and understanding what you might be able to do about that is the key thing that this provides you that like a normal network doesn't. And that gap, the argument I would make is that gap between how this average and tail latency performance is actually getting worse over time. But as we make networks faster and faster, we're able to get sort of good performance go really quickly, but then the poor performance still like lags behind it. So here's an example of sort of one of the consequences. That this is CDF of the total amount of bytes you're sending on your network as a function of the flow, sort of a CDF of this flow size, where at different amounts of network link speed. So this is for 10 gig links, and this is for 40 gig links, and this is for 100 gig links. And what you can see is, for an RPC dominated workload, we're reaching a point, roughly speaking, where not just almost all of the packets you're sending are essentially like, oh, almost all the RPCs you're sending are all small, like relative to the bandwidth delay product of the network. But actually most of the bytes that are transferring over the network are actually also small. So we went from a world where there's mice and elephants to one where there are mice and maybe some squirrels. And that's only going to get worse over time. And as a consequence, sort of end-to-end congestion control is no longer a reasonable thing to do. But this sort of RPC layer gives you this potential to say that you could do sort of some network layer congestion control, essentially control structure that's going to put on top of that. And here's some pieces that we've been building along these lines. So you think of observability would be one. It's like, oh, okay, what is the performance we're getting at these networks? Another is prediction. So how do we build something that's going to tell us what the performance we should expect out of the network, given that this is our workload pattern? The existing network simulation engines weren't going to give us this answer, so we built essentially an approximation engine that runs about 1,000 times faster than the existing systems. Another one is this notion of control. Yeah, go ahead.
So, like, wouldn't like historical logs be, how, like, if we take the historical logs as a simulation, like, how would you compare the accuracy of these two? Like, why would you not take, the historical log information and say, here's what we think would happen? Like, why would you do that?
So I think one of the challenges is you'd like to be able to understand how, as workload changes, be able to predict what will happen as a so if, for example, my load increases by a factor of 2 because I've just rolled out some new service that I think a lot of people are going to go use, or the pandemic hit, so therefore Zoom is going to consume some much larger amount of bandwidth, I'd like to be able to make some forward-looking prediction and not just a backward-looking diagnostic. Right? And so our goal is to be able to say, oh, this is roughly what you should expect to see given this is your workload, or this is what you should expect to see if I change my workload in a certain direction, or this is what I should see if I'm in David's case that he was talking about earlier, that where I'm now migrating a set of my underlying infrastructure in some direction. Okay, I've unplugged some wires and I'm plugging them in somewhere else. I'm in these quasi states where now my underlying infrastructure is different from how it used to be. So there are all those kinds of things I'd like to be able to do predictions for. And then I'd like to provide some sort of control structure that doesn't depend on essentially feedback mechanism from the network, or doesn't depend so tightly on feedback mechanism, because any feedback is likely to be only applicable over a long period of time as opposed to over the short time of a single connection or whatever. Anyway, so I thought I'd stop there because we run out of time, but any other questions we have? I guess, oh, the last part is, there's a lot of opportunity in application defined networking, and essentially it's like, oh, let's start from a specification, then try and understand how we can design an entire network stack that introduces, and actually possibly to answer this question that happened earlier, introduces both the things that application wants to be able to do for itself, but also potentially enforceable mechanisms like, oh, you'd like to be able to say that this network uses security or uses encryption, and you don't necessarily want to trust the application developer to do that for you. So there'd be also these things where there might be a trust boundary that you have to worry about. Again, why we build MRPC as a service rather than just as a library. But those things are ones that we also can explore. All right, so great. Thank you very much. Yes?
First of all, great direction from Ratul. Very much agree with the direction. I think just a couple of comments. One is traditionally, right, it has been, and I'm just wondering out loud, it has been really hard to give SLAs to applications. SLAs is a nice mental model, and it really helps us reason about things. But I've also been wondering why it has actually been hard to specify performance SLAs is what I'm talking about. There are many different kinds of SLAs, right? So that's a problem. I think that in itself is worth wondering. We often treated applications or in relative terms, like okay, this is more important than the other traffic. So when there is crunch, I'll prioritize something versus the other as as opposed to absolute SLAs?
Yeah, so let me try to answer those quickly so I can let Simon start talking, since that's also my work. So actually this drive of how we get application level SLA, how do we build something that will give us some enforceable SLA that the application can depend on is, I think, a hugely important task for the research community going forward. I think part of what's difficult about it is that we haven't had the right control knobs. It's like, oh, how would you go about doing this even if you knew? Prioritization is something that you could use, but it isn't super effective, and it really has this downside effect of everything that isn't prioritized ends up having much worse SLAs over time. So one of the things in the control loop could potentially be, how do you balance such that here's just the amount of prioritization you need to be able to accomplish your SLA, and therefore what other SLAs I might be able to also guarantee for someone who's maybe not the highest priority traffic, but also still important. Those are things that I think are possible to do in this sort of framework.
Yes. Sorry, one more comment before
Sure.
we're out of time. Okay. And ultimately, this has to be tied back to provisioning in some form, right?
Yes.
Because you can't have an SLA for an infinite amount of
Yes.
workload. So there is, as long as you're well behaved and within this, you'll meet your SLA, and otherwise no.
Yeah, so we haven't talked about this notion of, well, okay, we have these application level networks. What's the relationship of that to the underlying network? Does that make the underlying network simpler over time? Because now I can start negotiating not between a vast number of applications that we don't actually understand much about what their demands are, to one where actually I understand this is what's important to me and this is what's not important to me, that we can then start talking to the network in some reasonable way about provisioning.
Okay, well, thank you. I'm going to take over.
Talking about energy.
Thanks, Ratul. So we already heard it a number of times this morning that the scale of the cloud is absolutely massive. Well, the energy consumption of the cloud is also absolutely massive. Last I checked, we were at about 2% of national energy consumption among all national energy consumers, and that number is quickly rising. So we think that we should start to make the cloud aware of this massive responsibility that it has. So a move towards energy-aware cloud computing. How did we get here? Where are we going? Well, to understand that, let's look at computing energy efficiency versus the sheer demand for compute over time. And that's shown here on this graph. The blue line is the application demand for compute, and the black line is one that I hope you're all very familiar with. It shows energy efficiency per server, for example, per unit, as the black line here over time, and this is majorly affected by the slowdown of Moore's law. So effectively what you can see here is that when Moore's law was still going strong, we were able to keep up with the demand for computing by effectively just shrinking transistors and then getting exponential gains in energy efficiency. That has ended in particular with the end of Dennard scaling, which now means that we have this widening gap here between demand for compute and the energy efficiency that we can provide. And that means we have to build ever bigger, more massive data centers to keep up with that demand. In the recent past, in some ways, we have been able to mask this gap here somewhat by focusing on what I would call our equipment and facility-based solutions. Effectively moving workloads from on-premise into the core cloud allows us to share resources, which is more energy efficient than individual deployments. And we've also been focusing quite a bit on the facilities in the data center buildings themselves, so power distribution and cooling and so forth. In fact, some of the cloud operators in the core are so good at this that we're moving pretty close to a power use efficiency coefficient of 1, which effectively is ideal. That means that most of the power now goes into the actual servers and networks that are really powering our applications that we're running. And so the logical next step should be to continue to close this gap, to look at the software and the hardware itself. So to look at the servers and to look at the networks and to look at the software that's running there. And that's what we mean by energy awareness. So why might you care about this beyond just being able to kind of deal with this responsibility that you have? There are actually a number of effects here. The first one is that with this massively rising scale, we also have a massively rising cost of data center power infrastructure. Power distribution is the major factor in terms of cost when new data centers are being built. And standard operating procedure for building new data centers is to over-provision the power infrastructure, because you might not know a priori how many more servers you're putting into your data center. And this is where most of this massive cost is coming from. So if we could make our cloud energy aware, we could actually move from massively over-provisioning power to oversubscribing our power, knowing that most of the time the cloud is actually not very heavily utilized. Every data center is about, at best, 50 to 60% utilized. But in order to do that, we need mechanisms in place that are able to control load and control power consumption when we do have these spikes and redistribute the load and so forth. I'm going to go into a lot more detail later in this talk. Another factor is renewable energy. All of us are effectively pledging to be 100% renewable by 2030. Some cloud operators sooner than that. Well, guess what? This demand curve that I showed you on the previous slide is actually accelerating at a pace that's twice as fast as the deployment of new renewables in the United States. So if we ever want to get there and be 100% renewable by 2030, then we better close at least that gap, that 2x gap between the rate of deployment of renewable energies and the rate of growth for the cloud. Now, of course, that's not the only part to the renewable story. Access to renewable energy is also highly variable. Within a day, there are going to be swings of high carbon versus low carbon intense energy sources within the mix that you get out of the grid. And so not only is our power envelope for cloud operation shrinking versus the amount of load that we might want to run, it's also varying over time. And so again, in order to keep up with that, we need something that can automatically and at scale control the power consumption of a data center. Then there's power disruption. Climate change leads to more natural disasters, which leads to grid disruption. We're currently enveloped by smoke that's coming from some wildfires that are out in the Cascades. Wildfires regularly disrupt the power grid in California. Perhaps an even starker story here was the Texas winter storm 2 years ago, which knocked out the power for around about 5 days, and many data centers were at the brink of complete shutdown. And so just to look at some numbers here, I asked the core data center operators as to what they see their grid failures are. And these numbers are also from about 2 years ago, so I predict that these have actually risen as well. And they reported that grid failures are already, back then, were 4 times above the IEEE spec, which is used for the industrial and commercial power distribution building. And the mean time to recovery from these failures in the grid was back then 4.5 times above that spec. So I expect these numbers are actually bigger. And of course, that's not the end of the story. This is the core cloud where power distribution is generally much more stable. You might roll out your own power plant alongside your data center. This becomes much worse in the growing edge segment, in rural deployments, and in developing world deployments. And then finally, you might want an energy-aware cloud simply for more resilient operations and logistics. There are these so-called black swan events. COVID-19 was one of them. And there's the story that you can read in Wired about how Google observed a massive spike in Google Meet use because many people were moving online, about 30x in the first quarter of 2020, and they had to keep up with that. And the main problem logistically was actually not to provision all of these servers. It was to get the power into the data center to actually power all these servers to be able to run. And so again, if we had an energy-aware cloud, we might be able to actually prioritize these new important workloads that we couldn't predict would become important, and shed load from others so that we can make it much easier logistically to roll them out. And so that's the goal of this research agenda, is to make the cloud energy aware. And the first step to that is simply to make cloud energy software defined. So think akin to software defined networking, what that did to networks. We're trying to do the same for energy. What that requires us to do is to build a load energy feedback loop through the hardware software stack, energy so that we can observe what energy is being consumed, and also to identify where the energy is being consumed, the hotspots in our software, and load because that's one of the biggest knobs that we have in order to immediately control the amount of energy that we're going to consume at any point in time. And so that will bring about a fine-grained, short-term, and automated energy control at scale that we can then use to gracefully trade off power, performance, and quality of service for our cloud applications under the SLAs that we have with our customers. And so more concretely, what we're going to build and evaluate is a cloud energy control plane that is going to monitor cloud energy use at fine grain and at detail across the entire, like an entire data center and potentially across data centers as well, and then uses that according to developer-provided specifications to migrate load, shed load in order to stay within the power supply envelope that the entire data center is under. And so that will then, that will then bring about continued cloud scaling via more power oversubscription, make the cloud resilient to power variability, including power disruption events, provide continued operations resilience via power demand control, as well as provide much needed power supply and demand insights to us operators, but also this can be passed on to the developers and users. And there was a question over there.
Yeah, so the question for you is, I can see how you can get this cloud energy control plane to work for a first-party application where the owner of the application is incentivized to also act in the interests of the owner of the infrastructure. But it's much less clear to me how something like this functions when it's a bunch of random cloud applications and the people running those VMs really don't care about the power because that's the cloud provider's problem. So how can we, get either a line of incentives there, or what's the mechanism by which you get
a number of
VM owner to play ball?
Yeah, a number of thoughts actually. So let me actually start. There's kind of a variety of different applications that are built with a variety of different models, right? So they're not just VMs, which are very monolithic and generally hard to move and opaque. You can't really look inside of them. There's also applications that are built with like microservices and more nimble ways to build them. For those, I think we have much easier vantage points to kind of just take parts of the application, migrate that part around if we know that maybe it's not the most important, most performance relevant part for the application. That could be one thing. So I think starting with kind of more nimble ways of building software is maybe actually a good starting point. For the VMs, I think there are kind of two approaches that you could that we could do. One is just to align the incentives via new SLAs, right? So you could just provide energy efficient SLAs, carbon efficient SLAs to users, and they can then identify the cloud VMs basically that have this kind of slack to you, and that would be one way to do that. For the rest, I think this would be a great opportunity to partner with the machine learning faculty in the center, because what we can try to do is to understand what the SLAs or what the performance requirements of these VMs are by applying machine learning to them. That has actually been tried to some extent in Azure, for example, to try and understand what is the power profile and what is generally the SLA profile for a VM by applying machine learning to it. So that kind of covers the demand side of the why now question. Power control and power proportionality is, of course, a question that has been analyzed in the past. And traditionally, it's actually been difficult to get a good power proportional system. You can make systems power proportional to a certain extent, but if you look into kind of the research that has been done in the past, there's always been this limit where the idle power that was consumed by, say, a server, for example, would still be a quite big amount of the power floor that you could get to. Now, we think that there have actually been a number of technological advances that make it worthwhile to look now again at kind of power proportionality and power control, because these inventions actually allow both for a much more fine-grained power control, and more fine-grained kind of load migration across a data center, and also a greater power control dynamic range. So here are just a couple of these technologies. One is non-volatile memory, including battery-backed DRAM, and also disaggregated memories that can keep data accessible across entire server shutdowns. So you can get much faster restart from these servers. And that's one key ingredient in order to be able to be more power proportional, is to be able to shut entire CPUs down, memory down within a local server, effectively shut the entire server down so that we don't have to particularly run the fans of those servers anymore, and then bring them back very quickly. Disaggregated memory also helps with nimble migration of workloads, potentially even across heterogeneous types of CPUs, because they will all share that same piece of disaggregated memory. Then there are chiplets, and there's immersion cooling. Traditionally, being able to kind of at a very fine granularity control the power within a system on chip was difficult because there's effectively one voltage applied to that entire monolithic system on chip. But with chiplets, we actually get the ability to now completely shut off individual chiplets because they individually have their voltage that is being applied to them, and that allows for much more fine-grained power control there. And immersion cooling simply allows for an enhanced power control dynamic range because we get a much higher voltage and frequency range that we can explore basically with that type of cooling. SmartNICs have a similar effect in that they enable service without CPU involvement and memory access to a server's memory without CPU involvement, while themselves being heterogeneous compute devices that have a very different power profile than the server CPUs do. And so we can use them to migrate some of our services onto a SmartNIC while shutting down the server-side CPU and continuing to provide service that way. And again, enhancing our power control dynamic range via this type of heterogeneity. Finally, we have programmable switches, which will, we think, primarily help us with making this scale. Under certain circumstances, we might have to be able to react very quickly if there are demand spikes, which can happen within milliseconds, maybe even microsecond timescales. And for that, having just one centralized controller that has to kind of figure this all out immediately will likely not work. So the switches could be used, and the kind of hierarchical structure of a typical close-based data center network can be used to kind of compute power budgets and then send them out across the switches. We can then do local power control at a rack and at a pod level, for example. And of course, we can then also use some clever networking techniques such as power proportional load balancing. If we shut down servers, we can very quickly reroute requests that were previously going to these servers to a smaller set of servers, which typically provides additional energy efficiency. And so the agenda here effectively has 3 steps that build on top of each other. The first one is to simply provide software and hardware energy provenance. And we want to try to do this really down to the individual function. We want to know, like, not just which process, but really what is the function inside of this process here that is consuming the energy. And then also on the hardware side, we want to know where is this energy being consumed. Is this hotspot somewhere in the CPU? Is it in memory use? Is it in I/O or storage use? And so we have a number of ideas, and I just have some examples on here of what we're likely going to investigate. The first thing is to kind of look at the existing performance counters that we have in our CPUs and our other devices, potentially propose some new ones, and then build OS APIs and mechanisms, not just for OSs, of course, but also for hypervisors and so forth, that would allow us to get these insights from these counters. One, I think, key ingredient to this is that we need to build energy models that will basically be able to map from the performance counters, which are mostly performance geared that we have today, to actually allow us to make inferences about what the energy use is of a particular piece of software and the hardware components. And I will have an example, I believe, on the next slide about that. Once we have all of this information, we can then firstly just use that to make more energy efficient use of the data center resources. So for example, there is a lot of bloat in software that can consume a lot of energy. For example, if you look at, we had kind of in the previous talk, we looked at kind of RPC stacks with sidecars and so forth. There are a lot of different layers of the system stack that we go through. And if we can identify where most of the energy is being consumed in these layers, then we can use that to in turn build fast paths for these layers. And our groups have had some success with that from a performance perspective in the past, where we've been looking at kind of fast TCP stacks and things like that. We can also use this information to potentially unstrand some resources. If we, for example, know that there is some DRAM in a server that is not very heavily used, but yet that we have to keep powered because it's used to some extent, then we could look at trying to unstrand that DRAM and instead use disaggregated memory if that's amenable for the application. And again, the performance counters would help us with that in order to save that energy, to turn off that DRAM. And then finally, once we have that, we can use that to build the control plane and do SLA-aware energy optimization, which will then require us to build these scalable and extensible APIs and mechanisms to identify elasticity and migrate applications, as well as these policies that can do the same. That will then also involve using heterogeneous compute components like SmartNICs and so forth. We can even go as far as going into agile approximation techniques, and we think that machine learning applications are kind of perfect candidates for this because they're both a prime energy consumer, but also they can walk this trade-off spectrum between the amount of energy that is being consumed for a particular inference or training and the accuracy of the result. And we can get provable guarantees for what the accuracy is going to be for a particular amount of training or inference work that you're going to put in. Okay. Can I read it from here?
Apart from hardware and systems level abstractions, if you're thinking about programming language abstractions for cloud energy efficiency.
Oh, it's a great question. Yeah, so programming language abstractions. Firstly, let me say that this kind of control plane will likely involve a declarative way of specifying what should happen under a variety of power events, and I think we need a declarative programming language to do that. But yes, one could think further. I think within kind of the set of us, we are kind of more experts on the system side, which is why we haven't really investigated that at this point. But I do think that it's important to also look at programming languages techniques where the way that you write the program could tell you a priori that here is a kind of a hotspot that is going to emerge in terms of energy use so that you as a programmer could avoid making that energy mistake, basically. So that goes a little bit beyond, I think, the kind of solutions that we have in mind here, which is more from the systems perspective and what can we do from an operator perspective. But certainly, I think part of this bigger puzzle is that we should also make the cloud developers aware as they're writing software, how much energy might that consume. Okay, I hope that answered the question. So here are a couple of examples to just make things more concrete that we have embarked upon. In some cases, we're starting to embark upon. This one has been under work for a little while. So this first one here is called ePerf, akin to the perf tool that many of you might be familiar with, which is an application-level energy debugger and profiler. We're starting here, firstly, within the confines of kind of CPU-level investigations in a single server, but the idea really is to build this out to be an energy profiler that can operate at scale in the data center and really incorporate all these other devices. So the idea here is that as an application developer, your application may involve many microservices that run across many shared resources in the data center. But the support that you currently have from performance counters that deal with energy is often at a very crude level for your software to really figure out what might be going on in the program that you're writing. Typically, we can today measure at a CPU socket level, and I would say that's at best the case. What we really want, though, is to account for energy use not just in the CPU, but across devices, and then, of course, also identify that within our applications. Like, what does this RPC cost in terms of energy? And so ePerf makes that visible. And the way that we're doing this is by effectively looking at the performance counters that we currently have available, then building a model that infers energy use from those performance counters. And our current prototype uses particularly microarchitectural performance counters that measure things like TLB misses, cache misses, and so forth. And we then use the per socket level energy counters that we have, so Intel Ratul for short, to validate our model. And we can then use that model once we have measured one application to predict the energy use for other applications. And so in our evaluation, the way that we did this was by making use of the holdout methodology. So you might have a mix of applications that are running on your server. We take one out. measure its microarchitectural behavior and the energy that was being consumed, and then validate. We then get a number from our model as to what the energy is and where it's consumed in the application, and we then can use that to validate whether a mix of other applications is going to be accurately predicted by that model. And within that evaluation, we were able to stay within 6% error within a single socket server.
The program can go through phases, right? How do you know, how do you pinpoint one application could fire up an inference function?
Right.
That could consume a lot of power, then you decide to kick it out, versus another time when it is not.
Yes, so I think we will get there. So I think the current prototype, Tom will kind of give it a little bit more detail here, but the current prototype is able to do this at the process level. So I think it will not identify the different phases that the application is going through yet, but we will kind of investigate that as well. So this is still research that is in progress. Tom, do you want to add anything at this point?
The microarchitectural features are ones that you can collect fairly easily for small parts of your program or sort of for a phase. So, you know, you said, like, if your mental model is that your energy use of an application is primarily its memory access. So how many times it's going off chip to get the memory, how many TLB misses it takes or whatever. Those are things that you can use processor tools to be able to tie back to application.
Yeah, in the labs you can, but when you're running a customer's VM, it's not, you don't have access to all the information automatically.
Right, so that goes back to the VM question that we had before. I think there, what you'd likely want to do is to instead use machine learning techniques to figure out what the energy profiles of the VMs in phases, you could do that with ML as well, is going to be. There has been some prior art on that already. We're kind of starting our focus here with kind of microservices and things that are a little nimbler than the VMs.
I think the other question is who's the consumer of the information. So one possibility is that the person who wrote the VM, that is the person who's running the application, actually wants to optimize their energy use. And the other side is, can the cloud provider optimize the energy use of somebody who's just running? Well, maybe that's just a black box. There's nothing they can do about it. So I think we're trying to build tools on both sides of that.
You mentioned microservices. How do you reason about what will happen to the end-to-end application when you make some local changes?
No, I think that's also a similar kind of answer, which is I think that the provenance question of trying to trace information is very rigorous here. We get to say X-trace, but for energy.
So there will be used likely, there is X-trace and there is kind of other distributed tracers that have been built, and I think some of these techniques there apply. You got to kind of carry the information forward as something moves through the application in a distributed system. So there are a number of techniques that you can use for performance that I think will likely apply to kind of measurements of energy as well.
So one thing that becomes very interesting / tricky is when you have shared resources, right? And how you apportion energy. And I think the answer may depend on who you want the information to go to. For example, let's say that I'm running something that already activated a part of the hardware such that the next process that comes has very small marginal cost, right? So you could measure that and say, and tell the developer, hey, today your thing costs almost zero. But that's not useful if that person wants to optimize their software, because one day they're going to run by themselves, right? So it's useful to measure in one way if you want to maybe change the cloud scheduler.
Yeah.
But it's maybe you want another answer completely different if you want to tell the developer how to optimize their part, right? So I don't think there's a good answer to that, and maybe there'll never be. It depends. Maybe you have to be able to derive both answers, right?
Yeah.
Depending on who you want to give it to.
That's a good point. Yeah, I think in some ways that might be a counter argument to the programming languages solution that we were talking about earlier, which is mostly focused on the individual developer. If they run on an isolated server, they might see a very different power profile than what the cloud operator might observe. So depending on the point of the observer, basically, you might actually have different calculations that you might want to run, and you might need to optimize for each of these different parties individually with using different optimizations, right?
Yeah.
Yeah. So then here's another example for some systems building that we have done and how we might use that to enhance the power control dynamic range by making use of SmartNICs in this case as a heterogeneous compute device. So here the scenario is that we're building an energy-aware distributed file system. So let's assume that we have a node that is a DFS, a distributed file system replica, and it's running a file system that is actually migratable between a host CPU and a SmartNIC. We actually developed a file system like that called LionFS that won the Best Paper Award at SOSP 21. And so we can use that to actually look at, can we provide service if we want to shut down the CPU because we're in a power event and continue to provide service at an adequate rate. So that's the scenario here. So energy starts to become scarce for the server. And we want to shut down the host CPUs. If we have non-volatile memory in the server, then potentially along with that the DRAM, that's what the storage system is going to be interested in primarily, is the non-volatile memory. So we can put that into a high C state or into hibernation. And we can then, just before we do that, migrate the distributed file system from the host CPU over to the SmartNIC. And the SmartNIC can continue to access host local DRAM if it's powered on, and host local NVM, which is much lower power than the DRAM. And so we demonstrated that in an experiment where we shut down the host CPUs at a particular time. So we ran here the varmail benchmark out of the FileBench benchmarking suite on a distributed deployment of 3 servers, and this measures the overall performance as we were shutting down the CPU of one of these replicas. And so what happens here is at T8, at time T8, we shut down the host CPU, and you can see that the file system was actually able to keep service completely stable for this workload by just transparently migrating over to the SmartNIC, still providing access to the non-volatile memory in the server, and then we eventually at time T16 power the host CPU back up. Now, not all workloads are going to look like this because the SmartNIC is a much wimpier compute device than the CPU, so that's why in the control plane that we're going to build, we have to be aware of how much degradation there might be when we move a particular workload over. But for some workloads, you might see no degradation, where it's totally fine to do this, and you can shut down the server CPU. So this is another example. And then a final example of doing some energy-aware hardware building, we're also interested in looking at energy-aware disaggregated memory. Memory is another dominant energy consumer if you look at a server. It's typically CPUs and memory. And we have this new technology called CXL that will bring about cache-coherent disaggregated memory for these servers. And it's a great vantage point to look at the memory behavior of applications, because there will be kind of switches and memory controllers involved here that are external to the server that we, to a much greater extent, can open up and experiment with and look at the memory behavior, basically, that happens over this disaggregated memory interconnect. And so we can use that to model the performance of applications and then use that in turn to optimize our power consumption. For example, firstly, by just simply figuring out by how much can we reduce the amount of DRAM DIMMs that we need to deploy per server, just consolidate them, basically. The next level would be to do some more dynamic measurements at the external memory controller level, measure congestion there, and then do some replacement of applications according to how much they might care about congestion. Applications that have to wait on congestion will typically consume more energy because they're not going to get any useful work done, yet they're going to be stalled, they're waiting for memory access, and the CPU can't really shut down during that time. And then finally, we could also use some of this information and apply it to the disaggregated memory itself. In some cases, we might have pools of disaggregated memory that are not fully utilized, and we can figure this out and then, again, consolidate and maybe compress the memory that might have been previously distributed over a larger number of DIMMs to a smaller number of DIMMs in order to shut some DIMMs off and make that disaggregated memory effectively power proportional. Yes?
So I'm trying to actually place, there's many techniques that you went over, and I'm trying to like place them in some meaningful way in my head, right? So the first thing is, let's say you have 2 servers, and you're running one at 50% and the other one is at 50%. Right, so the first thing is shut off one and migrate that, right? So that's actually the base level server aggregation essentially that the inventor does pretty much, right? That ought to save a bunch of power, right? That's the first order. Right. The second order that we're trying to say is basically each server has 2 modes. One is actually the CPU is turned on, and then the second mode is basically you shut off the CPU and move to the smart NIC, right? Presumably, you are still operating two servers, except on the smart NIC and not the host CPUs. Okay, so that's actually still two servers on, but with smart NIC mode. Okay, so that's the optimization number 2. Is this actually a better optimization compared to the first optimization, which is to just consolidate the workload and shut off the second server?
I would say that's a whole trade-off space, right? So is it a better optimization from a pure energy perspective? No, I think you would want to do the consolidation, but in some cases you might still have resources that you might need to access that are on that server, and it might be difficult to migrate them away, right? Even with disaggregated memory, we're not likely going to be able to migrate anything at any point in time immediately, right? Because there are caches and so forth. And so in those cases, your next best option is to try and increase the power control dynamic range for that server, which currently is not great. I mean, we're basically stuck with dynamic voltage and frequency scaling at the moment, so a pure hardware level technique, and that can only go so far. So we need to go beyond that, and one way to do that is to be able to completely shut down, say, server CPUs and then also some server memory, and while still being able to access maybe non-volatile memory or storage disks that might be attached to that server. And one way to do that could be the smart NIC. So that would be a much lower power resource than using the host CPU.
So this is where the cluster level power optimization versus rack level power optimization versus server level power optimization.
Yes.
These are just three various.
Yes.
So within the rack, if you actually did the disaggregation with like JBODs and JBOFs and whatever, right, you can presumably turn off some CPUs while still accessing pretty much all that you need to access.
For some workloads, right? So I think that also has its limits, right? So you can disaggregate within limits. Some applications are going to require really fast access to their data. They will rely on local memory, local caches. And for those, the smart NIC solution is a good solution because you will be able to access that data still with a much larger power dynamic range, so you can shut down those CPUs. There's going to be other software that can mostly rely on large pools of disaggregated memory that's much more fungible software. And for those, just shutting down servers and relying on that pool of storage and memory that you may have might be the best solution. So I think it depends on the type of application that you're running. The latency sensitive ones are going to be the ones that you might still need to compute somewhere close to where that data is.
So this goes back to, sorry, technically just running late. Okay, you should take this on the section.
Okay, all right, yeah, this is actually my almost last slide. This is my penultimate slide. The broader outcomes here is that we want to make this real. So we'd like to demonstrate end-to-end solutions in real data centers, demonstrate agile, and by that we mean at most in seconds, maybe even more agile, for data center-wide power events, reducing the engineering cost to operating under future data center power envelopes, and improve cloud system software energy efficiency, which we think we can do by an order of magnitude, and power oversubscription also by at least a factor of 2. We're going to integrate this into production software, Linux, Zen, and just some examples here. And we want to build prototypes for hardware like power proportional switches, DRAM controllers, and disaggregated memories to help define their APIs and show their potential. And then finally, of course, these models will be immensely helpful as well. And that's all I have. So to summarize, cloud energy consumption is increasingly a problem, and we talked about the fallout of that. Our goal is to make the cloud energy aware, and we do that by building a cloud energy control plane. I'll show you a couple of examples of what we're thinking about that will become ingredients to that control plane, which will then bring about energy control, accounting, debugging, and instrumentation at scale. Thank you.